Now that we've had our introduction to forces, let's start talking about one of them specifically, the spring force. Not only are we going to talk about how exactly we can calculate it and analyze it, but we're also going to talk about why do we care? Why do we care at all about how exactly springs function? So let's go ahead and look at a very basic situation. Let's say we have a spring connected to a wall or something that's not moving, and on the other end of the spring we have what is known as a spring scale. And a spring scale is a device that literally just measures force. That is what it is measuring. So it's analyzing how much force is being applied to it. And let's say this is initially in a position where the spring has not been stretched at all, and the spring scale so is measuring no force. So basically, this is where the spring would sit naturally. And as we start to stretch the spring, so we move the spring, we stretch it some delta x. So its original position was at x equals 0, it's in position. It's now been stretched a bit. This spring scale starts to measure force because the spring is pulling back on the spring scale as the spring is being stretched. And if we were to graph this with the spring force on the y-axis and the displacement of the end of the spring, so how much the spring has been stretched on the x-axis, we would see that we get a nice, clean, linear relationship where the spring force is proportional to the displacement. Now remember, this just means proportional. And so if we want to get from being proportional to being equals, we need to multiply one of these sides by a constant. And to do that, we go ahead and say that, okay, F is equal to K delta X, where K is some constant, and that would actually be the slope of this line. It is the constant. So in other words, if I move delta X by 1, you would multiply that 1 times K, and that would give me my force. So this is the relationship we literally just described, called Hooke's law, named for Robert Hooke, who was an English physicist who lived about the same time as Isaac Newton, a little bit beforehand. And it's basically just an equation for the spring force, that the delta x and F sub s are directly proportional by some factor k. Now let's go ahead and mention all of the pieces here. So we have delta x, which is the displacement of the end of the spring. It is not the total length of the spring, it's how much additionally it's been stretched or how much it has been compressed. We don't care about the entire length. So this is specifically just how much it's been stretched or compressed, and we want that in meters. Now we need to be careful. A lot of times you'll get in centimeters, you want it in meters. The next thing we have is the spring force in newtons, because it is a force. And that's basically telling me how much force is exerted by the spring as it's being stretched or compressed. So if it's being stretched, it's pulling back. If it's being compressed, it's pushing back against you. And then lastly, we have this factor K. And this factor K is known as the spring constant, and the unit is newtons per meter, which makes sense based on the graph we were just looking at, that if you had newtons per meter times meters, the meters would cancel, we would get newtons. So a few things about the spring constant. The spring constant characterizes the stiffness of the spring. So if you have a bigger spring constant, that means you are basically, if you stretch it further, the spring is pulling back with a lot more force. So that would be a stiffer spring. If you have a smaller spring constant, and if you stretch a spring and you don't have much force coming out, then that would be a less stiff spring. So as K goes up, the stiffness of the spring goes up. Now one thing we want to be careful with here is that spring constant is, there's not like some pretty way to determine it. I mean, you could determine it this way, but there's not some magical formula for that particular factor. In fact, spring constants are usually measured in a laboratory of some sort. They are experimentally determined. So you would build a spring, you would analyze how much you stretch it and how much the force is being applied, and you could find it experimentally, and then you would know in future experiments, okay, this spring has a particular spring constant. So it is very much a spring by spring thing that depends on a variety of factors that you have to experimentally determine unless you're told what the number is because someone else previously determined it. Now, as we showed previously, F sub s and delta x have a nice, clean, linear relationship here. Now, we would expect that this graph should start at 0, the origin, because if you have not stretched or compressed a spring, there would be no spring force. And additionally, as we just mentioned, the slope would be the spring constant K in units of newtons per meter. And if you have a higher K, so that would be a steeper slope, more stiff spring. If you have a lower K, a lower slope, less stiff spring. Now, one thing we need to be careful with here is that if you were to realistically do this, it would not do this forever. Eventually, your spring would reach a point where it would start to flatten out. And what is happening there is that you are starting to deform the spring. You're basically, think about it like if you have a slinky, if you stretch it out way too much, eventually it doesn't really snap back. It's just kind of been ruined. So at that point, we would say that Hooke's law no longer applies. Because Hooke's law is a model. It has very specific limitations. It only works when we're looking at the portion of the graph that is linear. So that was what we would call working with ideal springs. Springs that have not been deformed or had any sort of thing happen like that. If it goes beyond this, like if we start getting in this region, we can't use Hooke's law anymore. But for this class, we're only going to be dealing with ideal springs. If we're going to go beyond that, you start going into a lot more engineering equations and techniques. So let's do a nice quick example. Let's say we have, for instance here, a block. It is connected to the spring. The block is originally at some position x naught at 0.20 meters, we'll say, from the wall. So that's basically telling you this distance here. And we know that the spring, we're told, it has a spring constant of 125 newtons per meter, and this is at the position where the spring is just sitting naturally, so there's no spring force. And let's say we now stretch the spring by moving the block to some new position, and we measure that when this occurs, the spring force is pulling back with 6.25 newtons. So we want to figure out what is the new position of the block. Now, if you want to try this on your own, go ahead and pause it, and then come back and let's see how you did. Hopefully you paused it and gave it a shot, but let's go ahead and work through this math. It's pretty straightforward. That we have our Hooke's law here, F sub s is equal to K delta x, and we want to find how much the spring has been stretched. So we want delta x, which would be F sub s over K, and basically just dividing the K across. And we know that the spring force is 6.25 newtons. The spring constant was 125 newtons per meter. You divide those through in your calculator, and we get 0.05 meters, or about 5 centimeters. Now, that wasn't technically what was being asked for, because that would be just this. If this is 0.05 meters, that would be our delta x, our change, the amount of stretch, but we were looking for specifically the final position. So I could just say, well, originally I'm at 0.2, I've stretched 0.05, I am now at 0.25 meters, and that would be the answer. Now, there's one specific thing I want to add on here, which is that remember, when we're looking at this, you stretch the spring to the right, but that means that the spring was pulling back to the left. So oftentimes, we will write Hooke's law instead like this. Instead of having our absolute value bars, you'll say F sub s is equal to negative K delta x. And what is this negative sign telling me? Well, the negative sign is telling me that the spring force is always in the opposite direction of the displacement of its end. So if I stretch the spring to the right, the spring pulls back to the left. Let's say I compress the spring to the left, well then the spring is going to push back to the right. That negative sign is just telling us the direction. So that is all that is indicating there. So for instance, in this particular situation, let's say we had said that positive was to the right and negative was to the left. So we would have displaced, we stretched the spring, so that would have been a positive delta x. So we see that we would get a negative spring force. So we could have said that the spring force was 6.25 newtons earlier when we said it, or we could have just said 6.25 newtons to the left. Forces are vectors, so we want to include the direction. If instead, let's say we had compressed the spring, so we'd had a negative delta x, well, that would have been involving a positive spring force, or we could have said that the spring was pushing with a force to the right. So as a final point, why do we care? This is something that really bothered me when I was in high school, which is that we were learning about springs, but I remember thinking to myself, I don't see springs that often in my everyday life. Like, I know they exist in some mechanical things. Like, I know there's springs in your car, there's springs on the garage door. I mean, occasionally I play with a slinky, but like walking around, not many springs. So what is the point of understanding them? And that's because they're actually around way more often than you think. Specifically, They are how we measure forces. Because springs can be so carefully calibrated, and the relationship between them and how much they're stretched or compressed and the force applied to them is linear, it's a nice, clean, easy relationship, we can actually use them to measure the forces we apply various places. For instance, this right here is a spring scale, just like we were talking about earlier. And in fact, you can see that there is actually a spring in the spring scale. So when we pull on this hook, you are pulling on the spring, and you pull it through some sort of certain distance, and that basically is calibrated, so whatever distance you pull it, you can read off some force from the spring scale. So I use it to measure essentially, I'm using that spring to measure how much the force I apply is. Now, that may seem a little weird because you don't see those too often, but any sort of scale you have used to measure, like, your weight, to measure the weight of something when you're cooking, to measure the weight of something at the grocery store, well, weight is a gravitational force. All of these involve springs. For instance, and this one here, you can't see it, but in this box in the back, there is going to be a spring. This spring is compressed by the weight on top of it, and as it's compressed, it causes the dial to turn some amount. And we can tell how much the force due to gravity is by how much it compresses the spring. Similarly here, there is some spring in the back here, and as this gets pulled down, it stretches the spring. The spring is calibrated, so we know how much the dial goes, how much force is applied. This is even true of old school bathroom scales. Old school bathroom scales would have springs in them that would be carefully calibrated so that you compress them when you step on them, and based on how much they compressed, they would be connected to a dial to indicate how much you weigh. Now, digital bathroom scales are a little bit different. Many scales that are digital now are a little bit different, but they have the same basic principle. They follow the same basic idea that however much they are stretched or compressed, you can easily calibrate to a certain amount of force, and therefore indicate how much force you are applying to it. So what are the main takeaways for this lesson on the spring force? Well, they're pretty straightforward. One, can I utilize Hooke's law? F sub s is equal to negative k delta x, or if you want to take the absolute values, you can, to analyze situations involving the spring force. Now remember, if you're using the absolute value bars, it's just going to tell you the magnitude of the force based on how much it's stretched or compressed. If you use the minus sign, it's going to tell you if it is pulled to the right or left, or whichever way you set is positive or negative. But no matter what, when we say spring force, you want a magnitude and a direction. Without that direction, it's not technically 100% correct. Additionally, we want to be able to analyze graphs of the spring force versus the displacement of the end, how much has been stretched or compressed, for specific situations involving the spring force. Remembering that the slope is going to be the spring constant k, and that helps us figure out, for instance, how stiff or less stiff a spring is, and additionally making sure that we are looking in the ideal portion of the graph. If it starts flattening out, we don't want to be analyzing that part.